direction and equal magnitude, same magnitude. So therefore we can say that these two vectors are equal. So next, zero vector or null vector. A vector has zero magnitude. So any vector has zero magnitude, then the vector is called zero vector or null vector. It is denoted by zero bar or zero. So null vector is nothing but magnitude should be zero. So this is called null vector. So null vector is denoted by zero or zero bar. So note that initial line terminal points of zero vector are coincide. So like this is as a circle. So start and ending point should be coincide. Okay, na? So these are zero vector. So once again definition is which has zero magnitude is called zero vector or null vector. So it is denoted by zero bar. So next 1.3.3 unit vector. A vector having magnitude 1 unit is nothing but magnitude is 1, then the vector is called unit vector. So how to find out the vector? A vector a bar is a vector, then a bar by mod a bar. So a bar by mod a bar is a vector with magnitude. This is called unit vector. So unit vector is nothing but magnitude should be 1. A vector is said to be unit vector. The magnitude of given vector should be 1. So this is called unit vector. Negative of a vector. A vector b bar, a vector a bar is a vector having magnitude. A bar is having the direction opposite to that. A bar is called negative of A. So negative vector is nothing but opposite direction. So a vector having its direction is opposite direction. So negative vector is nothing but it is opposite direction. Thus, this is called negative of a vector. It is denoted by minus a bar. So this is negative of a vector. So see here figures AB. AB direction A vector direction A to B. And so this is negative of a vector. So direction here B to A. So this is A bar, this is minus A bar. So these two vectors are opposite vectors. So this is AB, A to B direction, BA, B to A direction. So these two vectors are negative of a vector. A is negative of minus A, minus A is negative of A. Coinitial vector. We have the same initial point is called coinitial vector. So 0 to A and 0 to B. So this is 0 to A, 0 to B. So 0 to A is equals to A, 0 to B is equals to B. So are coinitial vectors. Non-zero vectors. A vector whose magnitude is not is equals to 0, then proper vector or non-zero vector is called proper vector or non-zero non-zero vector. So that is a vector has magnitude 0, then it's called zero vector. If the vector has magnitude not is equals to 0, then the vector is called non-zero vector or proper vector. Non-zero vector or proper vector. Rectangular unit vector. So rectangular unit vector. The rectangular unit in the rectangular coordinate system z direction I, j, k. So this is origin, x-axis, y-axis, z-axis. Uh, the unit vectors along the positive directions of x, y, z axis are called rectangular unit vectors. They, they are denoted by ijk means the direction of x-axis, direction of y-axis, direction of z-axis, respectively. The vectors ijk are mutually perpendicular, and they they form a right-handed system because screw rotates through 90 degrees from OX to OY will advance in the positive Z direction. So this is rotation of axis is 90 degrees. The rotation of axis is exactly 90 degrees to each and every axis. That is x to y axis is 90 degrees, y to z axis is 90 degrees, uh, y to x, x to y, y to z. So each and every axis rotation of vectors, rotation of axis is always 90 degrees. So it will form a rectangular unit vector. Next, algebra of vectors. So that is addition of two vectors. Addition of vectors. A single vectors whose effect in equal to the combined effect of two or more vectors is called result of the sum of these two vector. The process of finding the sum is called vector addition. If a bar and b bar are two vectors, then the sum is denoted by a bar plus b bar. The sum of a bar plus b bar can be founded by using the triangular law or parallelogram law. The sum of vectors, the addition of vectors, that is a comma b are two vectors, and the sum of two vectors is denoted by a bar plus b bar. So this is a bar plus b bar. So this is called addition of vectors. A should be should be a direction should be equals to b direction. A should be xyz axis and b also xyz axis. Triangular law of addition. If a bar and b bar are two given vectors, we first draw a vector A and place the initial point of B on the end point of A bar, joining the initial point of A bar to the end point of B bar. So we can obtain the sum A bar plus B bar. Graphically, A bar is equals to AB bar, comma, B bar is equals to BC bar, represents the two consecutive sides of the triangle ABC. The sum of A bar and B bar is given by the third side A bar, AC bar of the triangle. So this is called triangular law of addition. So these two sides AB plus BC, these two sides, addition of these two sides gives the third side of the triangle, that is AC, A plus B. So this is called triangular law of addition. The triangular law of addition, the sum of two sides of the triangle, the sum of two sides of the triangle is equals to the remaining side, that is third side of the triangle. It's called triangular law of addition. So that is AB, side AB plus side BC, that is equals to side AC. This is called triangular law of addition. Next, parallelogram law of addition. Here also same. If A bar is equals to AB bar plus B bar is equals to AD bar, represent the two adjacent sides of the parallelogram ABCD, then the sum of A and B is given by the diagonal AC. That so AB bar is equals to A bar, CD bar is equals to B bar. So the adjacent sides of the parallelogram, the two adjacent sum of parallelogram is equals to diagonal, that is AC. So here clearly AB is equals to A, AD is equals to B. These sum of two adjacent side of the diagonals is equals to the uh, diagonal AC. So that is sum of two adjacent of the sides are equals to the diagonal. So here the sum of two coinitial vectors is founded by using the parallelogram law. The parallelogram So this is mathematically also. So this is possible. Sum of two adjacent side of the parallelogram is equal diagonal. AB plus CD. So this is parallelogram law addition. Commutative law. Commutative law for any two vectors A bar and B bar, any two vectors A bar and B bar. So A bar plus B bar is equals to B bar plus A bar. So that is this is called commutative law of addition. A bar plus B bar is equals to B bar plus A bar. So this is called commutative law of addition. So let OA is equals to A and AB is equals to B. So in this diagram, OA is equals to A and AB is equals to B. So in parallelogram, opposite sides are so A plus B. A plus B is equals to OB parallelogram law. Sum of two adjacent side of the sides of the parallelogram is equals to its diagonal or triangle also is there. Sum of two sides equals to third side of the triangle. So this is in this OAB triangle. So we can see A plus B is equals to OB. So that is third side of the triangle. OA plus AB is equals to OB. So that is third side of the triangle. Here remaining also. In remaining triangle also, triangle CBO. In triangle OBC, ABC, OABC. So in this also same. So we can apply same mechanism. So that is same parallelogram law. So triangle law. Sum of two sides of the triangle is equals to third side of the triangle. A plus B is equals to OB. So therefore, from equation 192, A plus B is equals to B plus A. So this is called commutative law of addition in vectors. So next, associative law of addition. Associative law. So for any three vectors A bar comma B bar comma C bar, so A bar plus B bar dot plus C is equals to A bar plus B bar plus C. So this is associative law. Here also same we can take numbers. This OA this is A, AB B, BC C. So by using same here also triangular law. So we are getting first one A bar plus B bar plus C bar is equals to OA plus AB plus BC. So AB plus BC is equals to AC. So that is equals to OC. So next here also A plus B plus C is equals to, here also getting same, OC is equals to OC. So therefore from equation 192 we can write A bar plus B bar plus C bar is equals to A bar P A bar plus B plus C. So this is called associative law of vectors. Next, subtraction of vectors. The difference of two vectors A bar and B bar is denoted by A minus B. It is defined as sum of A and minus B. So where B is the negative vector of B bar. So thus A bar minus B bar is equals to A bar plus of minus B bar. So next, multiplication of vectors. Let A bar be a non-zero vector and M is a scalar. Then the product of A by B, A by M is denoted by M into A, or M into A is a vector whose magnitude is mod M times of the magnitude of A bar and whose direction is same or opposite of A according to as M is positive or negative. If M is equals to 0, then M into A is null vector. Is clear? So multiplication of vector is nothing but, so we are taking M is constant. So M is multiplied by some vector. So that is M is multiplied by A. So the magnitude of vector M into A is M times of A. So the magnitude of vector A is M times of A. Fine. Then if A is negative vector, in this case also same. So magnitude of A bar is uh, M times of A. So if this is both cases, if vector is positive vector or negative vector, in both cases the magnitude of A is equals to M times of A. Next, if M is 0, so 0 case is nothing but the vector should be 0. So therefore, it is called a null vector. Is clear? M times uh, product of a vector is nothing but M is any scalar is multiplied by a vector A bar. So A bar is a vector. So M is multiplied by A bar is nothing but M into A. MA is M times of magnitude of A. So both cases, positive case and negative case, M is a M multiple times of magnitude of A. If M is 0, so if M is 0, in this case, it is called zero vector or null vector. So this is multiplication of vector by scalar. So next properties of scalar multiplication of vector. The following properties are true for any two vectors A and B and any two scalars M comma N. So minus into A bar is equals to minus A. So this is called negative of a vector. So this is already discussed in previous. That is nothing but opposite direction. Opposite direction of a vector. It's not post multiplication. In this case, the vector value should not be changed, does not be changed. The vector value should be same, always same. The pre-multiplication of scalar or post-multiplication of scalar. So both values are equal. So that is m into a is equals to a into m. Pre-multiplication and post-multiplication of m is always should be equal. So next, n plus n into a bar is equals to m into a bar plus n into a bar. So this is nothing but, so this is like uh, multiplication. So m plus n into a bar, m into a plus n into a bar. So this is also equal. So next, m into a bar plus b bar is equals to m into a bar plus m into b bar. So this is next vector. Next, mn into a bar is equals to m into n a bar. So multiplication of properties of multiplication of vectors. So once again, minus into a bar is equals to minus a bar. So m into 0 bar is equals to always 0. So m into a bar is equals to a bar into m. This is always equal. M plus n into a bar is equals to m into a bar plus n into a bar. So next, m into a bar plus b bar is equals to m into a bar plus m into b bar. M into n a bar is equals to m into n a bar. Note, properties of addition of vector and scalar multiplication allows us to deal with the vector equations the same way as algebraic equations. If A is any non-zero vector, A by mod A bar is unit vector in the direction of A bar. It is denoted by A. A bar is a non-zero vector. A bar by mod A bar is a unit vector in the direction of A bar. This is denoted by A bar. So thus A bar is equals to A bar by mod A bar. So that is cross multiplication. A bar is equals to mod A bar into A. So that thus any vector A can be represented as scalar multiple of vector in its direction. So that is every vector should be represented as scalar multiple of a unit vector in its direction. Second point, the two vectors A and B are collinear vectors, implies and implied by we can write A bar is equals to some constant or scalar k into B bar, where k is some scalar. So two vectors are said to be collinear if and only if A bar is equals to k, some scalar multiple of vector k into B bar. Third one, if A bar comma B bar are non-collinear vectors and x comma y are scalars such that x into A bar plus y into B bar is equals to 0, then x is equals to 0 comma y is equals to 0. If possible, we assume that x naught is equals to 0. Simplify, A is equals to minus B by x into A bar. Therefore, A and B are collinear, which is not true. X is equals to 0. Similarly, we can prove that y also 0. Components of a vector. Consider a rectangular Cartesian coordinate system OX, OY, OZ with O as origin. So we know that I, comma, J, comma, K are unit vectors along OX, OY, OZ directions respectively. Let A bar be the given vector in three-dimensional, then A bar can be represented by a vector OP with initial point at O and end point should be B. End point should be P. Let X, Y, Z be the coordinates of P with respect to the rectangular system OXYZ. Draw P and perpendicular to the XY plane. Let NM, NQ be perpendicular drawn to y, x axis respectively from N. Hence, we have OM is equals to QN is equals to y, OQ is equals to MN is equals to x, NP is equals to z from the diagram. So OP can be written as ON plus NP. So OQ plus QN plus NP. So therefore, X into I bar plus Y into J bar plus Z into K bar. So every vector should be represented as Xi plus Yj plus Zk. These are the components of vector. This is called position vector of P. So this is position vector of P can be expressed as A bar is equals to Xi plus Yj plus Zk. So this is called position vector of P in rectangular axis, Cartesian coordinates. So where Xi comma Yj comma Zk are called rectangular components of a vector or simply components of a x vectors A bar in the x comma y comma z direction respectively. The scalars x comma y comma z are called rectangular components, simply components of a bar along ox comma oy comma oz respectively. Thus, for every vector a bar in space, there exists a point P in space such that a bar is equals to xi plus yj plus zk. Also given that P in a space, there is a vector QP. So QP also xi plus yj plus zk associated with the that. So therefore, there is a one-one correspondence between the vectors and the points in a space. With this understanding, we can write a bar is equals to x comma y comma z in terms of components. So therefore, mod a bar. So mod a bar is equals to root over x square plus y square plus z square. So this is called magnitude of a bar. So a bar is equals to root over x square plus y square plus z square. So this is called magnitude of a bar. Next, expressing a given vector in terms of position vector. So let A be let A be a given vector. Suppose A bar and B bar are position vectors of A and B with respect to origin. Then we have the following diagram 1.12. OA plus OB, OA plus AB is equals to OB. So OB is equals to OB minus OA, B minus A. So A bar is equals to A1I plus A2J plus A3K. B bar is equals to B1I plus B2J plus B3K. So AB is equals to B minus A. So that is B1 minus A1I plus B2 minus A2I J plus B3 minus A3K. So this is called components of a vector, position of a vector. Next, collinear and coplanar vectors. Collinear vectors and coplanar vectors. Two vectors are collinear if their lines of support are either same or parallel. If A and B are collinear vectors, their direction are same or opposite. Their magnitude may be different. They may or may not be co-initial vectors. If the two collinear free vectors have the same length as well as same direction, they are equal. So here we can see that which is AB and CD are not collinear vectors. So clearly AB and BC. Here BC also indicates. So therefore these two vectors are not collinear. Next theorem. If A bar and B bar are two collinear vectors, then each of them can be expressed as the product of uh, the other by a suitable scalar and conversely. So we know that A bar is equals to every vector should be multiplication of unit vector, product of unit vector. A bar is equals to mod A into A bar, comma B bar is equals to mod B into B bar. So where A and B bar are unit vectors along A bar and B bar directions respectively. If A bar and B bar are collinear, then A bar is equals to plus or minus b bar. Since mod A is equals to mod B is equals to 1, thus b bar is equals to mod B into B. So mod B by mod A into mod A into B. So mod A by mod B. So plus or minus mod A into A. So that is plus or minus mod B by mod A into A bar. So that is K into A bar. So therefore, K is any scalar. Conversely, if A not is equals to 0, by the definition of multiplication of vectors by a scalar, M into A bar represents a vector collinear with A. Hence, if B bar is equals to M into A bar for some scalar M, then A bar comma B bar are collinear vectors. Next, second theorem. If A bar and B bar are two non-zero, non-collinear vectors, and M and N are two scalars such that M into A plus N into B is equals to 0, then M is equals to N is equals to 0. So suppose if M naught is equals to 0, so MA plus NB is equals to 0. So we can write A is equals to M by N into B bar. If A is collinear to B by contradiction, thus M naught is equal M is equals to 0. So therefore, this is contradiction to our assumption. Thus M is equals to N is equals to 0 when M into A plus N into B is 0. So next, from the above theorem, if A bar and B bar are non-collinear, so M into A bar plus N into B bar is equals to X A bar plus Y B bar. So we can simplify M minus X into A bar plus N minus Y into B bar is equals to 0 bar. So M minus X is equals to 0, N minus Y is equals to 0. So therefore, M is equals to X, N is equals to Y. Is clear? In this case, M into A bar plus N into B bar is equals to X A bar plus Y B bar. So in this case, M is equals to X and N is equals to Y. So these two are equal. So next theorem. If A bar and B bar are two non-collinear vectors, then every vector are lying in the same plane determined by A and B can be uniquely expressed is of the form MA bar plus MB bar for some scalars M and N. So let O be the origin reference in A comma B comma R represented by OA, OB and OP respectively. Then OA comma OB and OP lies on the same plane. So in the diagram OA, OB, OP. So this is B. So this is A. So this is position vector R. Since OM and ON are collinear, OA and OP respectively, there exists a suitable scalars M and N such that OM is equals to M into OA bar. So that is equals to M into A bar. ON is equals to N into B bar. So thus triangle OMT by triangular law of addition. So triangular law of addition is shows that OP is equals to OM plus MP. So that is R bar is equals to MA bar plus NB bar. So this is the theorem. But we have to show that so this is unique. We can prove that uniqueness of the above theorem. So if possible, R bar is equals to M1 A bar plus N1 B bar. For the same scalar, for some scalar n1 comma n1 respectively. So therefore, if the two vectors are equal, ma bar plus nb bar is equals to m1 a bar plus n1 b bar. So m minus m1 into a bar plus n minus n1 into b bar is equal to 0. Since a bar comma b bar are non-collinear vectors. So therefore, so coefficients, these scalars should be equal. M minus m1 is equal 0, n minus n1 is equal 0. So therefore, m is equals to m1, n is equals to n1. So then there exists a vector r is equals to ma plus nb. So these two vectors are equal. If there exists any vector, so the scalar should be equal. M is equals to m1 plus r is equals to m2 plus m3. Any vectors. So, but the scalar should be equal. N is equals to n1 plus n2. N is equals to n1 is equals to n2 n3. So, therefore, the position vector r bar is always a unique vector. So, the vector ma comma nb are called components of r bar. In the addition of A bar and B bar respectively, A bar and B bar are called the base vectors in that plane. So this is called initial vector or position vector or position vector. R is called initial or position vector. So theorem. So next definition. Coplanar vectors. A set of vectors which lie on the same plane or whose lines support to as parallel to the same plane are called coplanar vectors. So we note that A bar comma B bar comma C bar are coplanar if there exists a scalars M and N such that C is equals to MA plus NB. A set of vectors which do not lie on the same plane or parallel the same plane are called non-coplanar vectors. The next theorem. So if A bar comma B bar comma C bar are three non-zero vectors, comma non-coplanar vectors, and m comma n comma p are three scalars such that ma plus nb plus nc is equal to 0. M is equals to n is equals to p that is equal to 0. We have to show that this one. So previous case. So here previous example ma plus nb is equals to 0. But here three cases are there. Ma plus nb plus pc is equal to 0. Suppose m naught is equals to 0. So we can write a bar is equals to minus n by m into b bar minus p by m into c bar. So by using the theorem 1.5.5 by the vectors lies on the same plane b bar or c bar. So that is m is equals to 0. So A bar lies on the plane P bar and C bar. It is contradiction to since A comma B comma C are non-coplanar. So therefore M naught is equals to 0. So which is contradiction to our assumption. So therefore M must be equals to 0. By similarly arguments, so we can also show that N is equals to P is equals to 0. Hence M is equals to N that is equals to P always 0. Here also same. Every vector can be expressed as linear combination of three non-coplanar vectors. So let O be the origin, P be any point in the space. OP is equals to position vector R in the diagram. So this is OP. So this is position vector. Let A bar comma B bar comma C bar be unit vectors in the three non-coplanar directions. OA comma OB comma OX, OY, and OZ respectively. Construct a parallelepiped and with OB as a diagonal. OA, OB, OC along OX, OY, OZ respectively as edges. So let OA is equals to X, OB is equals to Y, and OC is equals to Z. So then OA is equals to XA, OB is equals to YB, OC is equals to ZC. We know that from 1.16 R is equals to OP that is equals to OF plus FP. So position vector XA plus YB plus ZC. So now we have to show that. So this is uniqueness. Uniqueness means our assumption position vector R bar is equals to X dash A bar plus Y dash B bar plus Z dash C bar. If these two vectors are equal, so that is XA bar plus YB bar plus Z C bar is equals to X dash A bar plus Y dash B bar plus Z dash C bar. So next step. So therefore X minus X bar into A bar plus Y minus Y bar into B bar plus Z minus Z bar into C bar is equals to 0. So we know that theorem by previous theorem 1.5.5. So we can say that XA bar plus YB bar plus ZC bar is equals to 0 if and only if X is equals to Y is equals to Z is equals to 0. Here also X minus X bar is equals to 0, comma Y minus Y bar is equals to 0, comma Z minus Z bar is equals to 0. So therefore X is equals to X bar, Y is equals to Y bar, Z is equals to Z bar. So this is unique in coplanar vectors. The next note point, if R is called resultant of the vectors x a bar comma y b bar comma z c bar, so which are called components of R. Thus the numbers x comma y comma z are Cartesian coordinates of P with respect to the axis ox comma oy and oz. Second point, if ox comma oy and oz are mutually perpendicular, then a bar is equals to I, B bar is equals to Z, and C bar is equals to K. Thus, the position vector R bar is equals to Xi, A plus YB plus ZC can be written as Xi bar plus Y J bar plus Z K bar in the position of R with respect to origin. In this case, xi, comma, yj, comma, zk are rectangular components of R bar, and x, comma, y, comma, z are rectangular Cartesian coordinates of P. So discussed in 1.4.10. Next, third point. The above theorem enables us to add two or more vectors in addition of their components. R bar is equals to x1 a bar plus y1 b bar plus z1 c bar, and R2 is equals to x2 a bar plus y2 c bar plus z2 c bar. So addition of vectors. So that is nothing but uh, addition of two components vector R1 bar plus R2 bar, x1 plus x2 into a bar plus y1 plus y2 into b bar plus z1 plus z2 into c bar. Similarly, the result is applied from subtraction and scalar multiplication also. Next, show that the a, b, and c whose position vector 2i plus 4j minus k, 4i plus 5j plus k, and 3i plus 6j minus 3k from the vector vertices of right angle triangle. Solution. Let O be the origin of reference. So this is origin. So this is A, B, C. OA is equal AB is equals to, so AB can be written as OB minus OA. So that is AB. OB vector is given and OA vector also is given. So subtraction we are getting AB vector is 2A plus J plus 2K. Next, magnitude of this vector mod A is equals to root 4 plus 1 plus 4, 3. BC is equals to, so BC vector OC minus OB. So this is OC vector and OB vector. So which gives minus I plus J minus 4K. Magnitude of this vector minus BC mod BC is equals to root 1 plus 1 plus 16. So if that is equals to 3 root 2. So this is magnitude of BC. Next, CA. CA is equals to OA minus OC. So this is OA vector, this is OC vector. So magnitude of CA root over 1 plus 4 plus 4. So that is 9 is 3. So therefore, BC square is equals to AB square plus CA square. So by using Pythagoras theorem, hypotenuse square is equals to, so remaining sides square of remaining sum of squares of remaining sides. So that is in Pythagoras theorem. So clearly we can say that Given triangle is right angle triangle at A. Next, show that the points whose position vectors are minus 2a plus 3b plus 5c, comma a plus 2b plus 3c and 7a minus c are collinear. Let O be the origin reference and A, comma B, comma C are given points. Same here also. AB is equals to OB minus OA. We are getting AB matrix. OC matrix. OC vector. OC is AC is equals to OC minus OA. So that is equals to 3 into AB. So here 3 is common. We are getting AB vector. So therefore, AC is equals to 3 times of AB. So therefore, by using collinear definition, so we can say that AB and AC, these two vectors are collinear to each other. Collinear. Next, so 2i plus 4j minus 5k and I plus 2j plus 3k are sides of the parallelogram. Then find the unit vectors parallel to the diagonals. So given parallelogram ABCD, AB side, BC side. So we have to find out AC. So by using addition of triangle addition, AC is equals to AB plus BC. So this is AC vector. So direction magnitude of AC root over 9 plus 36 plus 4. So that is root 49, that is 7. So next unit vector along AC. So unit vector formula AC divided by mod AC. So 3i plus 6j minus 2k divided by 7. So similarly, BD. So BD is equals to BC plus CD. So BC plus CD can be written as minus AB. So CD is nothing but minus opposite direction of AB. So we are getting minus I minus 2j plus 8k. So mod BD, that is nothing but magnitude of BD vector. So root 69. So next we have to find out unit vector along BD. So BD is equals to BD divided by norm mod BD. So minus I minus 2j plus 8k by root 69. Dot product or scalar product of vectors. So next dot product of vector. If A if A comma B are two vectors, then the dot product or scalar product of A and B denoted by A dot B is defined as A dot B is equals to mod A into mod B cos theta. So theta should be lies between 0 to 180. 0 less than or is equals to theta less than or is equals to pi, where theta is smallest non-negative angle between A and B is given origin O. So this is angle. So this is OA, OB, AB. So angle between these two. So dot product of A dot B can be written as mod A into mod B cos theta. So angle should be 0 to 180 degrees. Note, by the definition of the scalar product of any two vectors in vector is a scalar. The dot product of any two scalar vectors is scalar. The scalar product of two vectors is proportional to length of the each and every vector. Theta is acute angle. A dot B is proportional is positive if theta is an obtuse angle. A dot B is negative. Next, properties of dot product. The dot product of two vectors is commutative. That is, A dot B is equals to B dot A. So dot product is always satisfies commutative property. That is, A dot B is equals to B dot A. So next, if M is a scalar, M greater than 0, M into A bar dot B is equals to M into A bar dot B bar. Next, M comma N are scalars. So M into A bar dot N into B bar can be written as M into N A dot B. So this is third property. So properties of dot product. So dot product is always satisfies commutative property. So that is a bar dot b bar is equals to b bar dot a bar. So next the second condition, m into a bar dot b is equals to m into a dot b. Next the third property, m into a bar dot n into b bar is equals to m into n. M into n is nothing but scalars. M into n a dot b. Condition for orthogonality. If the let a comma b are two non-zero vectors perpendicular to each other, then the angle theta between them, so that is pi by 2. If theta is cos theta is equal to 0, then we can say that a dot b is equal to 0. So therefore, a comma b are orthogonal vectors are perpendicular to each other. If the angle between two vectors are 90 degrees, then the vectors are called orthogonal vectors or perpendicular vectors. So we know that I, j, k are unit vectors along the three mutually perpendicular axes from the discussion above. Here also same. R bar is equals to R rj dot I plus R dot j dot j R dot k dot k. Next, if the two vectors are parallel to each other, A dot B is equals to uh, mod A into mod B. So in the same direction, A dot B is equals to A bar dot B bar, opposite direction. If the two vectors are parallel, then we can say that mod A into mod B same direction minus mod A into mod B opposite direction. Length of a vector. So length of a vector is a vector uh, A is a non-zero vector. A dot A is equals to mod A into mod A cos 0. So that is mod A square. So length of a vector A is equals to root over A dot A. The next distributive property for scalar product. The scalar product of vectors is distributive or addition of vectors for any three vectors A comma B comma C. A dot B plus C is equals to A dot B plus A dot C. Distributive laws. B plus A into dot A is equals to B dot A plus C dot A. So this is the distributive law of scalars. In next class, we will see. So this is previously discussed angle between two vectors. Theta be the angle between two vectors A and B. Then A dot B is equals to mod A into mod B cos theta. So we can write cos theta is equals to A bar dot B bar by mod A into mod B. Or theta is equals to cos inverse of A dot B by mod A mod B. So next class we will see examples on angle between two vectors.